Hello, everybody. Welcome to Algebra 2. Today, we are going to be looking at 3-6 theorems about the roots of polynomial equations. And generally, what we're going to be doing is learning how to factor higher degree polynomials using two methods. The first would be using a graph. Second would be using algebra. Using a graph is a great method. It works when your x-intercepts are real numbers, and really it works out really nicely when they're whole numbers. But sometimes our roots of polynomials are not always real, or the roots are not rational. And when that's the case, we need to factor them and solve using algebra. So let's start off with the graphical method. And we are on page 160 in your workbooks, but you'll notice the first two examples are not there. So I just want you to look at this as I work it out, and then I'll alert you whenever you should start taking notes in your workbook. All right, so if you're given a graph, so like this one, it's the graph of f of x equals x cubed minus 7x squared plus 36. And I want to factor it. So first of all, I'm going to look for the real roots, or for the x-intercepts. See one at -2, I see one at x equals at 3, and then another x-intercept at 6, 0. So that would make me think that this would factor, f of x would factor into x plus 2, because of the -2 right there, times x minus 3, times x minus 6. We did this a little bit in our other sections. Seems to work out well, and as I look back and reflect, I noticed the leading coefficient would be an x cubed, and if I were to multiply all the x's together, I would get an x cubed. Seems like I still have a cubic function, and if I were to graph f of x on Desmos, and then if I were to graph this version of f of x, you would find that they would align and be the same graph. So great, nice quick way to factor if all of your x-intercepts are real and if they're all whole numbers. It's not always the case. So let me show you this example. This one's not in your workbook, so I just want you to watch. It says from the graph, it appears that 4 is a 0 of the function p of x equals 8x to the 5th minus 32x to the 4th plus x squared minus 4. Without substituting, how can you determine if 4 is a possible solution? So it does look like 4 is an x-intercept, so that makes me think that p of x probably factors into x minus 4 times something else. Well, I can check with division, because if I divide p of x, so if I divide this by x minus 4 and get a remainder of 0, then p of x does factor into x minus 4 times whatever would be left. So let's try some synthetic division. I'm dividing by x minus 4, so I put a positive 4 in the little box. The coefficients of p of x are 8x to the 5th, negative 32, x to the 4th. There are no x cubed, so I need a 0 placeholder. There is 1x squared. There are 0 x's and a -4. And I'll zoom out so we can see everything. All right, then I'm going to add, bring down that first 8. Okay, 4 times 8 is 32. That was a -32. -32 plus 32 is 0. 4 times 0 is 0. 0 plus 0 is 0. 4 times 0 is 0. 1 plus 0 is 1. 4 times 1 is 4. 0 plus 4 is 4. 4 times 4 is 16. And -4 plus 16 is 12, which is not 0. So that means this point right here is not 4. It's probably really, really close, but it's not 4. Maybe like 3.999998, but it's not 4. And I know that because I did not get a 0 as my remainder, so not 0. Okay, so that means I can't factor that way. My other thought is like maybe this would be 1, but then again, like maybe 0 is an x-intercept, but look at this scale. Negative 200, negative 400, negative 600. There's a good chance that's not on 0. And I can also look and see in the equation, this term right here doesn't have an x, which means I wouldn't factor out an x in the front, and so it's not 0. Okay, so we can't use a graph on this one. Man, because that other method made it so nice to factor. All right, so when that happens, we're going to rely on something called the rational root theorem. So here's what it is. Here's what it's formally written as in your book. It says let p of x equal this expression, and basically what this is saying is the a's and the subs, like this part, those are coefficients, so this is a coefficient. So like an is one coefficient, an minus 1 is the next coefficient, and a sub 1, that's the next coefficient. So the a parts are just coefficients. X to the n, x to the n, x to the n, those are the variables. So really what it's saying is pretty much you have a polynomial. So let's just make up a polynomial in place. So let's say p of x equals 5x to the 4th plus 3x squared plus 7x plus 2. Okay, so just say you have a polynomial. The coefficients are integers, so coefficient here, coefficient there, and coefficient there. Those need to be integers, which means they're positive and negative whole numbers. If the polynomial equation equals 0, so if you set it to 0, if it has any rational roots, then each rational root is of the form p over q, where p is a factor of the constant term a sub 0, and q is a factor of the term a sub n. So let's get some highlighters here. Okay, here's the things we need to focus on. P is a factor of the constant term. So P would be the factor of 2, and then Q is a factor of the leading coefficient a sub n. Right there. Okay, so what this is saying is that if P of x has any real roots, real x-intercepts, they're going to be of the form P over Q, where we talked about P. Okay, so let's look at example 1 so you can start writing some of this down. And you probably should write down the rational root theorem. And I suggest you write this part down because that's what you're going to need to remember in your workbook. Okay, so example 1 says list all the possible rational roots for each equation. And you can think of rational solutions as possible rational x-intercepts, because we were talking about graphs. So let's keep talking about graphs. So if I were to graph y equals 4x to the 4th plus 13x squared minus 124x squared plus 212x minus 8, if I were to graph that, let's list all the possible rational x-intercepts without me having to graph and look. All right, so here's what you do. You need to take the factors of, let me grab my highlighter again. We're going to take the factors of the constant term, and then we're going to divide them by the factors of the leading coefficient. So I'm going to start off by saying possible, nope, not possible, factors of 8. And we don't have to worry about the negative. We'll take care of that in a minute. Factors of 8. So factors of 8 are 1, 2, we'll divide evenly into 8. 3 won't divide, but 4 will divide. 5, 6, 7, and 8. Possible factors are 8. Now, 1 is a factor of 8, 2 is a factor of 8, 4 is a factor of 8, and 8 is a factor of 8, but we also need to consider the negative factors as well. So we'll say plus or minus 1 is a factor of 8. Positive and negative 2 can also be divided evenly into 8. Positive and negative 4 can be divided evenly into 8, and positive and negative 8 can be divided evenly into 8. So we're going to take those factors, and then we're going to divide them by the factors of 4. A little bit larger because that's this coefficient. So factors of 4 are positive and negative 1, positive and negative 2, and positive and negative 4. So when I divide those, so this was the P part, this was the Q part. When you divide those, you get all the possible rational roots of that function. And also think of it as possible rational x-intercepts. So I need to divide. So I'm going to divide each factor of 8 by each factor of 4. So I'm going to start by dividing 1 by each of the factors of 4. So 1 divided by 1 is 1. So that's positive and negative 1. 1 divided by 2 is plus or minus 1/2. 1 divided by 4 is plus or minus 1/4. 1 divided by, oh, I already did 1 divided by 4. Okay, so now let's take the factors of 2 and divide them by the factors of 4. So 2 divided by 1 is 2, so plus or minus 2. 2 divided by 2 is 1, but I've already listed that one. 2 divided by 4 is 1/2, and that one's already listed. Okay, now we're going to take the factors of 4 and divide by, 8 and divide it by the factors of 4. So 4 divided by 1 is 4, so plus or minus 4. 4 divided by 2 is 2, plus or minus 2. 4 divided by 4 is 1. And I already have 2 and I already have 1, so I don't need to list it twice. All right, now let's take the factors of 8 and divide it by, 8 divided by 1, 2, and 4. 8 divided by 1 is 1, so plus or minus 8. 8 divided by 2, plus or minus 4, which I've already written. 8 divided by 4, plus or minus 2. So now I have a list of all the possible rational roots of that polynomial. So what I'm saying is if I were to graph this function, if it has any rational x-intercepts, they'll either happen at a 1 or negative 1, 1/2 or negative 1/2, 1/4 or negative 1/4, 2 or negative 2, 4 or negative 4, and 8 or negative 8. If you don't believe me, pause the video, go graph this, look at the x-intercepts, and see if any of those listed are possible, are the x-intercepts on the graph. So pause the video right now, go check it out on Desmos. Now, some of your questions on your assignment just ask, what are the possible rational roots? So that's why we're doing this on example 1. All right, moving on. B is the same way. So now we're actually going to use the rational root theorem. So let's start with, actually, let's go into example 3, because example 2 is a word problem. We'll come back to it. Let's do example 3. Find all the complex roots. Okay. All right, so I'm going to try to find all the complex roots. So we're going to start, I'm going to try to factor this. I'm going to try to factor. And I see, oh my goodness, there's so many terms here. I've never factored anything like this. But the way that you factor it is with the rational root theorem. Now, if I can find 1, 0, then I can factor the rest. Okay, so let's, first of all, so to try to factor, if no other method that you've ever done before, like sum and difference of cubes, greatest common factor, factoring the trinomial, if none of those work, then you can apply the rational root theorem. So if we're going to try to factor, the first thing I need to do is I need to list all those possible rational roots. I'm going to list them. So that means I need to take the factors of -2, or just factors of 2. I'm going to divide them by the factors of 3. And that's going to equal my possible rational roots. Okay, so factors of 2 are 1 and 2, so plus or minus 1, plus or minus 2. Factors of 3 are 1 and 3, plus or minus 1, plus or minus 3. So let's find our possible rational roots. 1 divided by 1 is plus or minus 1. 1 divided by 3, positive and negatives considered, plus or minus 1/3. 2 divided by 1, plus or minus 2. And 2 divided by 3, plus or minus 2/3. Okay, so if this equation has any real solutions, then it's going to be one of these 8, and there's 8 here because I have a positive and negative, one of these 8 rational roots. So step 1, list possible rational roots. Check. Boom. Step 2, find a 0. How do I find a 0? Okay, well, one thing I can do is I could graph this and look and see which one's a 0, or I can find a 0 by guessing rational roots. So I could pick any of these 4 possible rational roots, do synthetic division, see which one is going to give me a 0 remainder. So let's try with synthetic division. Let's see. So let's pick a rational root. Let's try -1. Coefficients are 3, 4, 2, -1, -2. Okay, bring down that 3. 1 times 3 is -3. 4 plus -3 is 1. -1 times 1 is -1. 2 minus 1 is 1. -1 times 1 is -1. -1 plus -1 is -2. And -1 times -2 is +2. Oh, look, I have a 0. So that means, so far, I can say that this factors into x plus 1, because remember, it's the opposite of this number, x plus 1 times 3x to the third plus x squared plus x minus 2 equals 0. And so this is now this equation right there. All right, so I have factored it a little bit. I'm trying to solve for x, haven't factored it completely. So then what do I need to do? I need to find another root. So I go back up to my list because I can't factor 3x cubed plus x squared plus x minus 2. I can't factor that using grouping because grouping is not going to work for this one. I won't be able to factor out a greatest common factor binomial. So I'm going to look back here and I'm going to see, okay, well, let me pick another root. It's a really good idea to pick positive 2/3, and I'm telling you this because I have tried it before. And basically what you're doing is you're picking which, like guessing and checking by doing synthetic division. Pick any of these 8. If you get a 0 as a remainder, you can continue factoring. So we're going to pick 2/3. So I'll do 2/3 here. I'll use my new coefficients, 3, 1, 1, -2. Bring down the 3. 2/3 times 3 is 2. 1 plus 2 is 3. 2/3 times 3 is 2. 1 plus 2 is 3. 2/3 times 3 is 2. -2 plus 2 is 0. So now that means that this factors, I've got this x plus 1 that gets brought down. I have the x minus 2/3. And now from this part, I have 3x squared plus 3x plus 3 equals 0. And then, oh look, the 3x squared plus 3x plus 3 has a common factor. So I can factor it even more. X plus 1 times x minus 2/3 times 3 times x squared plus x plus 1 equals 0. And then x squared plus x plus 1 will not factor any further. So now I go to solve. Set each factor equal to 0. X plus 1 equals 0. I get one root is x equals -1. X minus 2/3, set that equal to 0. I get 2/3. 3 does not equal 0, so I don't have to set that one equal to 0. But then I can set x squared plus x plus 1 equal to 0. Doesn't factor, so let's try quadratic formula. So A is going to be 1, B's 1, C's 1. So we'll say x equals -b, which is 1, plus or minus the square root of b squared, which is 1 minus 4, times 1 times 1, all over 2 times 1. Okay. So x equals -1 plus or minus the square root. It's going to be 1 minus 4, which is -3, all over 2. So x equals -1 plus or minus I square root of 3 over 2. Whew. All right, let's zoom out and take all that in. Look at all that work. Oh my goodness. Okay, so what do we do here? We tried to solve. So we found the possible rational roots. I used one of those possible rational roots to factor. Then I looked and noticed this part had 4 terms, so I used another rational root to factor. So I got to this part, and then solve each factor, but then we had a quadratic equation that didn't factor, so we had to solve. So how many solutions do we have here? 1, 2, and then the plus or minus 3, 4. So there are 4 solutions total. 2 of those solutions were real. And notice, -1 is an option, and so is positive 2/3. And then 2 solutions are imaginary. But altogether, we had 4 solutions. Which brings me to the point of the fundamental theorem of algebra. Here it is. It says, if a polynomial has a degree of n greater than or equal to 1, then when you set that polynomial equal to 0, it has n solutions. So here's a tip. This is really handy when you're solving. The degree of this polynomial is 4. So whatever that degree is, that's how many solutions you have when you set it equal to 0. So look, 4 solutions, and now we had 4 solutions.